This is section 2.4, what impacts strength of evidence. So we've learned how to do hypothesis tests. Today we're learning what happens if just one number changes, okay? Really, this is just to help you develop your intuition behind hypothesis tests, okay? So let's remember we had a woman from Scotland who claimed the ability to tell if a person had Parkinson's disease based on their smell. So they had 6 people known to have Parkinson's disease were a teacher, and 6 people that didn't have Parkinson's were a teacher. They collected the shirts, they tested Mill. Mill correctly identified 11 of the 12 shirts as belonging to a person with or without Parkinson's. So let's remind ourselves, the research question was, can Mill correctly identify whether a person has Parkinson's disease by smell, or was she guessing? So that's a research question. The null hypothesis was that she was guessing, or that my pi equals, let's see, she had a 50-50 chance of guessing, right? So 0.5. Wait, let's use our notation. Our null hypothesis is that pi equals 0.5. The alternative hypothesis is that she can tell, and if I use my symbols, that would be the H with the A, that pi, or my logarithm proportion, is, let's see, if she can identify by smell, she should be getting more than 50% correct, right? So we want to do more than 0.5. Let's see, so she was correct 11 out of 12 times. We can find a proportion for that. So 11 divided by 12 gives me 0.9166. Okay. And we found that the chance of her randomly guessing correctly 11 out of 12 times is only 0.0032. Okay. Or if you look at the p-value, there's only 0.032 chance of her getting that many or more correct if the null is true. If she's just guessing, it's only 0.032. So we're pretty sure that she's not guessing. Okay. Now, interestingly, she was only wrong on one shirt, and she was adamant that that shirt came from a person with Parkinson's. 8 months later, that person was actually given a Parkinson's diagnosis. So she actually figured it out before the doctors did. Okay, but for us, the interesting thing is now, if she's correct 12 out of 12 times, then now my p-hat, my proportion, is going to be 12 out of 12, or 1. Okay, so what is our new p-value? So now, if I go all the way up to 12, and I look for 12 or more, we're all the way down to 0.0002. Okay, so we got even smaller. So when we had a test statistic that was farther out in the tails, okay, that makes our p-value even smaller. So what we want you to remember and learn is the farther you get on the tails, if your statistic is farther on the tails, your p-value will be smaller. So if your sample statistic p-hat is farther from the hypothesized null proportion, which in our case was 0.5, then the p-value gets smaller. So the farther our observed proportion is from the hypothesized null proportion, so 1 was even farther away from 0.5, the smaller p-value, or statistics farther in the tails give us smaller p-values. Okay. Now, on the test, we will ask you questions like this, of what would happen if you change from this statistic to this statistic, okay? And you can remember that the farther you're on the tails, the smaller p-values. But let's say you get on the test and you freeze and you can't remember, okay? You can't always use the applet on the test. So just bring up the applet, find the p-value for the first situation, then find the p-value for the second situation and compare, and there's your answer. Okay, so if you forget these rules, you can just do the whole thing and find the p-value by hand and get the right answer. Now, this is very important. Okay, so this is two-sided test. So far, we've only been teaching how to do one-sided test, and we just didn't tell you there was another option. Okay, but this other option is very common. You'll see it all the time in research. Okay, so let's say, for example, we have a coin that's damaged, or we think it's probably not fair, but we don't have anything that makes us think the probability of heads is too small or too big. We don't know, are we getting more than 50% heads, less than 50% heads? We're not really sure what's happening. We just think that it's not fair. So we do what's called a two-sided test. So the null would be something like, the coin is fair. That's always our status quo. The alternative is what we're suspecting, what we hope to show. So the coin is not fair. But let's put it into symbols or figure out what our proportions would be for each of those situations. So the null would be that my pi equals 0.5. The alternative, I'm not really sure. Do I think that my pi should be less than 0.5, greater than 0.5? I really don't know. So I just put a not equals to 0.5. Okay, so I just want to see is it not fair. That means it might be greater than 0.5 or less than 0.5. So let's toss the coin 100 times and we get 45 heads, or p hat equals, let's see, 45 out of 100 gives me 0.45. So let's do a one-sided test and a two-sided test to compare our results. Okay. So on the left side, I said, well, what if I think the probability of heads is less than 0.5? So my alternative is now pi is less than 0.5. So when I put into the applet, I did 0.5 as my probability of heads, 100 tosses, I did 1,000 repetitions, and I counted what's the chance of getting, oh, well, that's not good. Sorry, again, first time I used these notes, I said 45 heads. We actually need to do 40 heads to make it match our results. So 40 heads, okay. So I counted if I got a proportion of heads less than or equal to 0.4 because I want to show that my true proportion is less than 0.5. So anything less than 0.4 would be even more suspicious. So I count less than or equal to 0.4. When you look at the results, here's my p hat of negative 0.4, sorry, and it gave me a p-value of 0.0240. Okay, so my p-value is 0.0240. But now, if I want to show that it's just not 0.5, okay, I put in everything the same. Now this still says less than or equal to 0.40. I could have greater than or equal to 0.40 because notice there's this option box where all I have to click is two-sided. Okay, and if I click that two-sided, now notice what happens. It did everything less than 0.4 and it did everything greater than 0.6. So 0.4 and 0.6 are the same distance from the 0.5 in the middle. So it did everything in this tail and it did everything in this tail. And now let's look at that new p-value. Now it's 0.0470. Okay, I just want to show you on the applet. So if I put in the 0.5, 100, and 10,000 and I looked for as extreme as less than or equal to 0.40. So here's the options. I click on the two-sided. Notice now it will do both tails for me. This p-value is a bit different than what we got before because before I only did it 1,000 times. And so there's a lot of variation from time to time. If you don't like getting different answers from me, always go out to like the 10,000. You'll be getting more precise answers. But it's just this two-sided. You don't have to do anything else between these checks or anything else. Just truly click two-sided. It'll give you the areas in both tails. Now, let's just see, what do I get if I multiply that one-sided p-value of 0.024 by 2, so 0.024 times 2 should give me 0.048. Now, notice what did I get here? 0.047. The difference here is only because it's a simulation. Theoretically, they should be exactly the same. So what happens is you have one tail and then you have the other tail. They're both the same size of the tails. So the p-value will always be double. Okay. Now, the p-value is always double if you do a two-sided test because you just do both tails. So it's always going to be double. Again, very common in research. They don't know which direction they think the hypothesis should go. They just look at both tails. So if you don't have a reason to think the alternative hypothesis should be a less than or greater than, you just do a two-sided test. But because you look at two tails, you always get a p-value that is twice as big. You know, accounting for rounding and simulations, if we did this theoretically or like a million times, they would be exactly double. Okay. Now, the other thing we want to know about is sample size. So this is very important too. So do you remember when we flipped coins to see how many heads we would get back on page like 34? So I'll fix that. It's example 34 on page 23. So we could have a computer simulate flipping a coin 1,000 times and keep track of the proportion of heads. Remember, in the beginning, we can't really predict how many heads we would get, but as we flip the coin more and more times, the proportion got closer to what we'd expect at 0.5. And you can go back and look at those notes if you don't remember this. Okay, but like the first time we flipped it, we got one head, and 1 out of 1 actually gave you a proportion of 1. Then we got some more tails and heads, and our proportions of heads just kind of goes all over until eventually we do it enough times so we even out at that like 0.5. So I want to ask you, like, would you be surprised to get 6 or more heads at 10 tosses? Well, at 10 tosses, we're probably like right about here. 6 or more heads, that would be a p hat equals 0.6. Like, are you really surprised to get something at like 0.6 right there at 10 tosses? I would say, like, no. At 10 tosses, like, there's still lots of times I might have more than like 6 out of 10 heads. Okay. What about 60 or more heads at 100 tosses? So if we go up at 100, would you be surprised if you were at 60 or 60% or more? I would say yes, right? Like, I don't see any zigzags by the time I get to 100 as big as 0.6. But what about at, oh, this is supposed to say 1,000 tosses. Okay, so at 1,000 tosses, by the time I come out here to 1,000, would you be surprised to get a sample proportion of 0.6 or more? Well, yes, by the time we got to 1,000, we were like exactly on that 0.5 line. I would be so surprised if someone told me they got 0.6. So surprised. So very, very surprised. So for smaller samples, we have a lot more variability and unpredictability. So but larger sample sizes, there's less variability. Our samples should be much closer to what we expect. Now that's a little background to why it matters for hypothesis tests. Okay. Now let's see. We can also use our one proportion applet to simulate tossing the coin 10 times repeatedly and look at the possible sample proportions. And we can do it again for 100 tosses and 1,000 tosses. And I put them all on the same scale. So here's the distribution of the possible sample proportions. Okay. And I told you the SD of all of these possible sample proportions. So for 10 tosses, my SD is pretty big. Also, it kind of looks like a normal curve, but it's not quite filled in all the way yet. Okay, at 100 tosses, it's pretty filled in. It looks like a normal curve. My SD is only 0.05. And at 1,000 tosses, this is still a normal curve. It's just squished so much to be on that same scale that it doesn't really look like it, but it is a perfect normal curve. Okay, but my SD is all the way down to 0.016. So you can see as you do it more and more times, the variability of what you can get shrinks. Okay, and so you can have a lot of variability at 10 tosses. By the time you get to 1,000 tosses, there's hardly any variability left. Okay, and so how does this relate to p-values? Okay. Well, coming back up, p-value is just like, would you be surprised? So at 10, would I be surprised if I got 0.6 or more? No, I wouldn't be surprised. By the time I got to 100, no, or yes, I'd start to be surprised. By the time I got to 1,000, I'd be very, very surprised. I'd have really, really small p-values. So what this means is that bigger sample sizes give us smaller p-values. Okay, like for the same sample proportion. Like, so if everything else stayed the same, but you got bigger sample sizes, you're going to get much smaller p-values. Okay, because the p-value is the area on the tail. So if I'm like right here, and the p-value is the area on the tail, that's going to be pretty big. But here, well, that's like this area. I'm probably about this far because we're on the same scale, or like the area out here on that one. So the area is just getting smaller and smaller and smaller because there's less variability. So let's actually do the 3 hypothesis tests side by side to see if a coin is fair or not. Okay, there are 3 people with 3 different coins, but they toss their coins a different number of times. So person 1 happened to get 6 out of 10 heads, person 2 got 60 out of 100 heads, person 3 got 600 out of 1,000 heads. They should all have the same null and alternative hypotheses though. So the null hypothesis would be that the coin is fair. And in symbols, that would be that my hypothesized proportion is 0.5. Okay. Now the alternative, do I think, well, let's say that the coin is not fair. But did they tell me that we suspect that it should be greater than 0.5 or less than 0.5? No, it didn't tell me anywhere if we think it's less than or greater than. So this is an A. It should be that pi is not equal to 0.5. Or we're going to look for like, is the proportion not 0.5 or different from 0.5? Okay, so this one's going to be two-sided. Okay, because again, they didn't tell me if I thought it should be less or greater, so we're just looking for, is it different than? Okay. Let's see, so let's fill out this chart. Sample size for the first person's 10, next person's 100, next person's 1,000. Okay. And if we were to find p hat for the first person, it's 6 out of 10, so 0.6. The next person is 60 out of 100, so 0.6. And the third person is 600 out of 1,000, so 0.6. So they all have the exact same sample proportion. They all have the same hypotheses. The only thing that's different is the sample size. Okay. And I did all the simulations for us. Remember, you just click that button that says two-sided when you have the two-sided. Let me show you that button again, just right here, the two-sided button, and it'll give you the area in both tails. Okay. So when we have sample size of 10, my p-value is 0.7505. So that means if I only toss 10 times, I have a 75% chance to get 0.6 heads, or something farther away, like 0.6 or more, or 0.4 or more, if it's a fair coin. Okay, completely plausible. This is a big p-value, very plausible. Is there evidence that the coin's not fair? No. Okay, we didn't find any evidence for the alternative. The null is plausible. There's no evidence for the alternative. Okay, nothing exciting happening. But now let's go to person 2. Again, they got a sample proportion of 0.6, but their sample size is 100. Okay. So now I have a p-value of 0.0584. Okay. So now there's only about like a 6% chance that they would get their results if the null is true, if the coin is fair. Well, 0.0584, that is actually getting fairly small. Like maybe we're starting to get like some evidence, like I might be a little bit suspicious, but we're not enough to put us over that threshold. So it still counts as a big p-value. So is the null plausible? Yes, it still has like a 6% chance of happening, of getting our data if the null is true. And so is there evidence that the coin is not fair? No, but we were getting pretty close. Okay, if you have studies where you're like, oh, that's kind of close, like I don't really know, what they should do is just go get more data, go get a bigger sample size, and then they'll be able to tell better. Okay, but person 3 at 1,000, now what's their p-value? It's basically 0. So that's a very small p-value for sure. What that means is if they toss the coin 1,000 times, there would only be about a 0% chance that they could get a sample proportion of 0.6 or something more extreme. Not plausible at all. And is there evidence the coin is not fair? Yes, lots and lots of evidence. That is a very small p-value. Okay, we have lots of evidence for the alternative. So this is why we like bigger sample sizes. By the time we get bigger sample sizes, there's a lot less variability. We feel more confident in our results. We get smaller p-values. We get better, like stronger evidence. So if everything else is the same, if p hat is the same, increasing the sample size will give you a smaller p-value. Okay. Oh, and I put in this remark. So what do you do when the p-value is right at the threshold 0.05? So in a situation like this, I'd probably say something like, we don't have quite enough evidence to say that the coin is not fair, but it's still close. I think we should collect more data before we decide for sure. And very important, we always report and publish our findings, no matter the p-value, even if the p-value is huge. This helps other people learn from our results. Sometimes it can be just as important to be like, oh, like the null is plausible. We were hoping to show the research out. The alternative hypothesis is true because that was our research question. But sometimes it's just as valuable to be like, oh, we thought that this would happen, but it actually didn't. Okay, that still helps other people learn. Okay. One more example. Let's flip some coins 100 times. The first coin got 55% heads. The second coin got 65% heads. Let's test each coin to see if we think it's fair or not. Okay, so the null is that pi equals 0.5. My alternative is that pi is not equal to 0.5 because I didn't tell you if I thought it was less or more. We're just doing a two-sided hypothesis. We can write down our sample proportions. The first one would be 0.55. The next one would be 0.65. But either way, though, our hypothesized proportion is that the coin is fair, so 0.5. Okay, you'll notice my applet gets set up the exact same way. My probability of heads is 0.5, 100 tosses. I'm going to do 1,000 repetitions. And here I looked at the proportion of heads instead of number of heads. So I want something as extreme as 0.55. But the other one, I want something as extreme as 0.65. Okay, click that you want a two-sided. And now notice, so here is 0.55. There's a lot of area in the tails. But if I go out to 0.65, there's a very small amount of area out in the tails, right? So my p-value for the first one is 0.3710, and my p-value for the second one is 0.0030. So when I go farther out in the tails, I get smaller p-values, and that's just our reminder here. So remember, getting sample proportions farther away from our hypothesized null proportion of pi equals 0.5 means we get smaller p-values. So most of this was just to help you develop your intuition, okay, except for those two-sided tests. Very important, very common in research. You need to know that you have that option of doing a two-sided test.